Thank you for the nice introduction. Just this morning, we heard a nice talk of Camille Poisson. She's also working on, or she worked on this interaction between the processing atmosphere and the materials, and actually I do the same. Today, I talk about the reactivity of titanium-containing powder blends in LPBF under different reactive atmospheres. And I do so because in my PhD, I focus on the interaction between the process atmosphere and the liquid melt pool. And therefore, I use reactive atmospheres like CO2 and N2. And I want, with this interaction, to produce particle reinforced materials in situ during the process. And this process can be divided into two steps. The first step is the dissociation of the gases in the uptake in the liquid melt pool. The second step is then the precipitation during the solidification of our materials. And we assume that the first step, the uptake process of the gases, is the most critical, because in LPBF we have a very low liquid lifetime, which means that we won't be in equilibrium between the processing atmosphere and our material. And secondly, as I want to work with iron-based materials, their equilibrium solubility in the liquid state is quite low. And so the gas uptake is limited. And what we can do against is, for example, alloy with reactive materials like titanium. And as the interaction of iron-based materials with the atmosphere is quite low, usually we said, okay, let's do a really extreme experiment with titanium-64 in the CO2 atmosphere. And as this is quite reactive, like I said, okay, be careful at the beginning and print titanium-64 samples on the argon atmosphere. Then I removed the uppermost powder layers to only do a remelting and change the atmosphere to CO2. And what happened then during the remelting under CO2, you can see in the following video. So what you can see is a relatively exothermic reaction here. You can even see that the hot spatter, which is flying around, is so hot that it can start a new reaction, which you can see on the stoner. But the nice thing is, at least I have, due to the remelting, some reaction at the surface of my samples. We can see clearly a difference between the remelting and the original surface. The question which arises now is, if I now want to process iron titanium blends in LPBF, can I do that at all in CO2? And this talk is about to answer this question. And first of all, we have to understand what happens. And it's actually quite obvious, because we see that the reaction is initiated by laser exposure. It's very strongly exothermic and self-sustained, which means that even after the laser was turned off, this reaction went on until all of the powder was consumed. And it's really important to know that this reaction occurs in the powder bed only, because powder has a very high surface to volume ratio, which means it lowers the activation energy of this reaction, and furthermore, it has a very low thermal conductivity. So the first step is now to investigate this reaction for pure titanium. And we do that with our Cognitive 3D Plus, equipped with two lasers up to 1000 watt laser power, a 3D scanner unit, which enables me to use different spot sizes between 80 and 500 microns, and scan speeds up to 12 meters per second. The only question is now, how can I control this reaction? And if you understood what happened, it's actually quite easy. So I only had to do a special substrate plate where I put in some drill holes, filled in the powders, and then I expose them with the laser. And so you can see I have the reaction under control. And for my, which is now called ignition, I use different scan strategies. The first is a very short exposure strategy it's only a small line of 500 microns. And the other is a bit larger one of 5 to 5 millimeters, which is called square. What you can see is now in the results is I started with my line exposure strategy. So I use different beam diameters going from 100 to 500. And for each of these beam diameters, I set a certain scan speed and determined the minimum power I need for ignition. So I said go up 10 watts per 10 watts until I saw an ignition. And what you can see is that we have linear correlation. On the y-axis here, I use the power normalized by the beam diameter and the layer thickness. What is here, of course, hypothetic, but I set it to 30 to only get a number for the energy density for which this reaction occurs. And if we do now a fitting of this curve, we can see that the slope represents the activation energy of this, or not the activation energy, but at least the energy density I need to really cause this reaction. And what you can see is that which is not counterintuitive, but with a smaller beam, I need more power than with a larger beam. And the reason we suppose is that a larger beam has a larger contact area to the reactive atmosphere, which is then the reason for these findings. So now, until now, we only use these short lines, but actually what I want to do later on is to print massive parts, or at least some larger ones. So I have to increase my exposure area, and that's what I do with this square exposure strategy. And here, I want to show you one experiment which serves perfectly well in understanding what happens in the powder bed. So here I use the energy density, which is extremely low, only 1.6 joule per cubic millimeter, for which one scan cannot lead to an ignition. You can even see that I can scan 30 times without having any reaction. So please focus now on the exposed area in the video in the middle. So after 50 times of scanning, you can see it gets brighter and brighter and brighter because we have heat accumulation. You also can see that here after the scan that we really have in the middle kind of a heat accumulation, also how it looks in 3D. And now it's getting interesting because what happens if I do 70 times scanning? Because I increase the scan time, and here I have more and more heat accumulation until I see a reaction. And this shows that it's actually the temperature. The temperature in the powder bed is high enough, then I get this reaction. And furthermore, what it shows that heat accumulation reduces the necessary energy input for the laser for ignition, because now I have seen a reaction for 1.6 joule per cubic millimeter due to heat accumulation. Let's take a short look at the microstructure. What we can see is we have a layered microstructure consisting of a reaction layer, a molten layer, and a sinter layer. And this microstructure is due to a thermal gradient which we have in our material, because the reaction is driven by the contact with the atmosphere. And if we take a closer look to this reaction layer, we can see the formation of three or many different intermetallic phases. We can see that we have a titanium oxide layer, we have below a layer of aluminum oxide, alpha titanium, and titanium carbide, which is very well visible in the EDS spectrum of aluminum, where we have three regions. We have one region where we have an enrichment in aluminum, one where we have a depletion of aluminum, and somewhere where we have in between, which is the alpha titanium. So we are now going and using what we learned and apply this on iron titanium plants. But before we do, we look at some equilibrium processes, some normal science, I would say. And what I did was a TGA BSC, which is connected by this black long tube to an IR cell. So I heated titanium-64 and iron powder up in an argon and CO2 atmosphere to 1,400 degrees Celsius centigrade. And what we can see is that under argon, the weight stays more or less stable. Whereas under CO2, both powders show an increase in weight of 39 and 67 weight%, fitting very well to the intermetallic phases titanium oxide and iron oxide. And now it's really important to mention that, like poor iron powder, as you can see, reacts with the CO2 atmosphere, but it cannot be ignited by no chance. So I used really 1,000 watt and everything I could, and it did not work. And the reason, therefore, we learn on the next slide. But before, what we can learn is that during the thermal analysis, we can measure the emission of carbon monoxide. And this is because we have here the dissociation of the carbon dioxide into carbon monoxide and oxygen. If you remember, we could see in the ignition product, I would say that we have some carbides in there. So in this process, we had the participation of carbon here in the equilibrium plot. And more interesting is that exactly at the time or at the temperature where we have the highest oxidation rate, of course, we have also the highest heat release, because these oxidation processes are very exothermic. And if we now compare the oxidation enthalpy which gets released during this process of titanium and iron, you can see that this one of titanium is way more larger, what everybody actually knows. But I want to conclude here that if I now use a mixture between both, then I will find a composition for which no reaction takes place, because we have seen that titanium reacts, iron does not react. So there must be a mixture in between, and that's what we do now. And therefore, I prepared different mixture ranging from 70 to 30 atomic %, and I exposed them with an extremely high energy density of at least 10 times the amount what I would need to ignite pure titanium. And we could see that for 70 atomic percent titanium, we still have reaction, so nothing new. But what happens if I now go down to 50 atomic percent titanium in the blend? What you can see is that we have still a reaction, but propagation is limited. And this is due to that the heat conduction from the reaction front is larger than the heat release, so the reaction will stop after some time. But still, that's not what I want, because I do not want to see any of this later on in LPBF. So I have to go into 30 atomic percent titanium, and here you can finally see that I have no reaction anymore. I have some thermal degradation of the powder, but okay, who cares compared to that what happened before. The only question now is what happens if I increase the power, because before we have seen that increasing the power can lead to an ignition. And to really convince all of you that this is really a safe limit, and to be absolutely sure, I now use 900 watts of laser power, leading to an energy density of 240 joules per cubic millimeter. You can see that we have a lot of fireworks, a lot of spatter, and a big hole in our powder bed, but at least I found a safe limit. And now I owe you one last answer. This is the answer to the question if this also happens in nitrogen atmosphere. And as you might think, the answer is yes. You can see even more colorful ignition products. You can see on the backside of the ignition products the golden color of titanium nitride. Yeah. But the more interesting thing is if we compare CO2 and N2 atmosphere. And what we learn is that titanium powder is not that reactive in nitrogen than it is in CO2, which is also very important information for me for my future projects. So let me conclude my results. First of all, the LPBF titanium 6,4 in a CO2 and N2 atmosphere leads to a self-sustained and highly exothermic combustion reaction. There's also no parameter combination for which I can process in the densely titanium parts in CO2 atmosphere, and probably also not in nitrogen, because I have heat accumulation during the process, and so after maybe 10 layers, 20 layers, who knows, we will have this reaction. The reaction starts if the temperature is very high, or is higher than it is, or reaches the temperature for the ignition, and continues until all of the powder was consumed for pure titanium. The onset of the reaction is very dependent on the laser parameters, but also affected by heat accumulation, which can lower the necessary energy input for this reaction. Very important for me is that I can process iron titanium binary powder blends up to a titanium content to 30 atomic percent. And I learned that this titanium containing powder blends are less reactive in nitrogen atmosphere compared to a CO2 atmosphere. And with that, I will end my talk. So thank you very much.